Hi there, this is Penelope. This is a video for DE 4102. This is a question from Topic 10, Class 3 from the handout, question 8. Now, just note that if you're working from the handout itself, it's got a missing symbol. That pi and 20 pi m cubed is missing, so make sure that it's there in your workings. Right, what we have is a cylindrical can, and we need it to hold 20 pi cubic meters. The material for the top and the bottom cost 10 meters squared, $10 per meter squared, and the material on the sides, that's around the curvy bits, costs $8 per meter squared. And your question is to find the radius and the height of the can that is the cheapest to produce. Okay, so we know, because we're told, that the volume is 20 pi. Now, we also know that the volume of a cylinder can be written as pi r squared h. So it's the area of the circle times the height. Now, those two things have to be equal. So 20 pi h must be equal to pi r squared h. And if we rearrange that, we get that if we rearrange the second one rather, we get that h is equal to 20 pi over pi r squared, which we can simplify to 20 over r squared. What we need to do now is to write ourselves a cost statement, putting in the $10 for the top and the bottom and the $8 for the sides. Now, the top and the bottom are circles, and each circle has an area of pi r squared. And the sides, well, that's the circumference of the can, 2 pi r times h. So if we put all that information together, we're going to get our minimum a cost statement. And we know that we need to minimize because of this word most economical. So it's going to be the cost of the bottom, the cost of the top, and the cost of the side. So putting those in formula forms for the circles at the top, the bottom, and then the surface area for the side, we can get that. So $10 for the top, $10 for the area of the bottom, and then $8 per square meter for the area of the side. And don't forget now that C is going to be in dollars. Now we can simplify that. We can add the first two terms to be 20 pi r squared, and we can sort out the third term to be 16 pi r h. Okay, that's fine. What we need to do to minimize is to find the derivative of that. But of course, there's a problem. We've got two variables, so we need to go back to what we had to start with and use the fact that h is 20 over r squared. So we substitute it in. Then we have a statement which needs tidying up, needs some cancelling out, but it will give us a cost statement without h in it. So there we have our cost statement, 20 pi r squared plus 320 pi over r. That is what we have to differentiate in order that we can then find the minimum for the function. Differentiating it gives us 40 pi r minus 320 pi over r squared, and we need that to be equal to 0 for the minimum or the maximum. Okay, fairly easy rearrangement. 40 pi r equals 320 pi over r squared, and if we rearrange that, we can get that r cubed is 8, and then it's a simple matter from there to get that r is equal to 2. And if r is equal to 2, we put that back into the original, and we get that h is equal to 5. Now, that's all the question asked, except that it did ask you to find the minimum cost. You were asked to find the radius and the height for the most economical can, which means the minimum cost. So we have to prove that those two values will give us a minimum, and in order to do that, we need to find the second derivative. So finding the second derivative, we get 40 pi plus 640 pi over r cubed. That's got to be positive for a minimum, which it actually is. If you think about that, if r is positive, which it has to be because it's a length, then any value of r is going to make the second derivative positive, so it's positive. That means we do indeed have a minimum. Now, the question didn't ask you to find the cost. Sometimes it will. So that means then that you need to put r equals 2 and h equals 5 back into the cost function. Use your calculators, and leaving it in terms of pi, you'd get 240 pi. But to three significant figures, that's $754.